A very warm welcome to all my viewers. In today's video, we are going to discuss the study of nuclear counting statistics when the number of counts are high. So for today's experiment, the apparatus that we need is a GM counting system, a GM detector stand, a GM detector tube and a source. The source may be beta or gamma source. Now the question is, what exactly are we trying to accomplish in this experiment? The principle of this experiment is based on the central limit theorem, which states that when a large sample size has a finite variance, the samples will be normally distributed and the mean of samples will be approximately equal to the mean of the whole population. Here, mean is the numerical average of all the given samples and variance is how deviated a value is from the mean. In simpler terms, when we take a very large number of trials at random, we get the result in what is called a bell curve. Now, in this experiment, we are going to take 100 readings of the radiations emitted by a radioactive source and we are going to study the nuclear counting statistics when the counts are high. We will also verify whether or not the result that we obtain at the end is a Gaussian curve or not. But how exactly do we count the number of radiations of a radioactive source? So if you remember, in the beginning of the video, we were talking about GM counting systems and GM stands and GM detectors. So these GM counting systems, or Geiger-Müller counting systems to be precise, is what solves our purpose. Named after the scientists who made them, these powerful and efficient machines count radioactive radiations based on a very simple concept, that is ionization. This has a metal cylinder which is filled with a gas, usually inert like argon. The metal cylinder acts as the cathode. There is a thin metal wire stretched along the axis of the tube which acts as the anode. When the correct potential is applied and the radiations from the source enter the tube, they knock out electrons from the gas atoms and in turn the knocked out electrons knock out other electrons from the other gas atoms. This causes an avalanche effect. As all the electrons rush towards the anode, a current is produced and based on the voltage recorded, the number of particles responsible for this voltage can be counted. This is how the GM counter works. There is a threshold below which the tube does not work. After this, the number of pulses is proportional to the voltage. This region is known as the proportional region. If the applied voltage is increased further, then a point will be reached after which the count rate remains constant over a certain region. This region is known as the plateau region. This region is used for Geiger-Müller operation. Beyond the plateau region, the applied electric field is so high that a continuous discharge takes place in the tube and the count rate increases very rapidly. It does not require any ionization event to happen. So, the tube must not be used in this region. That concludes the theory and principle for this experiment.
Now, let us see the procedure of the experiment. First, set up the GM counter in its standard procedure. Now, switch on the GM counter and the power on. Then press the program button. On the screen, you will be able to see time and voltage. Now, you have to set the time up to 10 seconds by using the arrow present on the GM counter. And now, you have to set voltage up to 450 volts by using the knob given and also ensure that you should not turn the knob very quickly. So now you have set the time 10 seconds and the voltage 450 volts. Now we have to take the background count for this experiment. Take the first reading without any source and press the start button. Record the number of background counts for 10 seconds and repeat the same for 3 trials. Now let us place the source. The source used here is cesium source. Use a pair of forceps to place the source in the plate. Don't touch radioactive material with your bare hands. Insert the source at the fourth slot. With the same settings of time 10 seconds and voltage 450 volt, press start and take the readings. Repeat the same procedure for 100 trials. Now reduce the voltage to 0 volt by turning the knob on the GM counter and switch off the GM counter. We have recorded the trials, so let us see how to tabulate the readings. In this first table, the first column is the observation recorded from the counter. Corrected counts Ni is calculated by deducting the background counts from the measured counts. N bar is the average of all corrected counts, also known as the mean. The next column is filled by calculating Ni minus N bar. The standard deviation sigma is calculated by square root of N bar. The next column is calculated using the following formula, that is Ni minus N bar divided by sigma. The calculated values are rounded off to the nearest whole number and this is filled to the last column. Using this data, we construct another frequency distribution table. The graph of rounded off values and frequency distribution is plotted and that comes out to be like this. Observe the graph displayed on the screen. The curve has a bell shape. Now, what do we interpret from this bell curve? This graph shows that when the counts are high, we get a Gaussian curve, which denotes a normal distribution. Hence, this is the result of our experiment.
With this, we have come to the end of our video. Thank you for watching.